about the critical angle here? All right. So just a little refresher on this business. Let's imagine that we have an interface between two media. Okay, looks like that. And we'll also have a normal. Okay, and basically what we want to talk about is, let's say that this is a fast medium and this is a slow medium. So this might be deep water and this might be shallow water. Okay. And if we have an incoming wave, if we are going from fast to slow, we will bend towards the normal. Okay? We covered this, the mathematics that we deal with here. This is just review from yesterday, but the mathematics that govern this. So we've got V1, so this is the velocity here. We've got wavelength 1. And we've got sine theta 1. This is all the incident angle side stuff. Okay, and then we've got V2, theta 2, and sine theta 2. So we have a law that tells us the relationships between these things. And essentially, it's just this. V1 over V2 equals lambda 1 over lambda 2. That's wavelength equals sine theta 1 over sine theta 2. Okay? So this is part 1. Okay? Some people might refer to this as Snell's law. Snell's law definitely factors into this. There's one more kind of piece to Snell's law, which we'll get to in a minute when we start to talk about light. But this is true of all waves. So we have incident wave fronts hitting here, and they change direction when they get into the new medium. One thing that maybe would help you to understand this is imagine that you have a wheel and axle scenario. Like let's say you took your Tonka truck apart and you had the axle and the two wheels. And let's imagine that this is the pavement and that this is your your lawn. So there's grass over here. So obviously the wheels are going to roll more freely on the pavement than they would on the grass. If they come in contact here, okay, well, this wheel is going to slow down before this wheel does. Just like this side of the wave is going to slow down before this side of the wave. So when it comes in contact with the grass, it slows down, right? And this keeps on. And so what would happen is it would actually change direction as it contacts, exactly like what happens with the wave. Okay? This slows down before that end does. I mean, if you start to slow this end, it makes sense that this is going to curl around. You're going to get a new angle when you go on to the new area. Okay, so let's get into this concept of critical angle now and see if we can nail it down. What is with my pen? It's going crazy. There we go. Okay, so critical angle. All right. So let's say that we have shallow water now on this side and deep water here. And let's say the source of the waves is over on this side. Okay? So we now have waves coming from shallow into deep. Okay? So what we're going to have is a bending away from the normal. Okay? And what we're doing here is we're coming from a slow velocity into a faster velocity. Okay? And theta 1 is now here, and theta 2 is now here. And what we have to consider is that if you increase this angle, you by consequence also increase this angle. Eventually, you're going to increase this angle such that it becomes perpendicular to the normal or parallel with the surface. Okay? The angle at which you increase this, okay, such that this becomes 90 is called the critical angle. Okay? And Any angle larger than the critical angle will cause the the waves to essentially bounce off the surface and reflect back inside the medium. Okay, so once this refracted angle gets larger than 90, you have reflection back into the medium. And when that happens, we call this total internal reflection. Okay, and the waves cannot escape. So let's just lay down our values here and see what we can do. Okay, so this is V1 now. This is V2, right? Because we're coming from here, and so we're going to have wavelength 1 and wavelength 2. So what we can say here is that sine theta 1 over sine theta 2 should be equal to V1 over V2. Okay? Now, key here, let's pick some values, is that this is slower than this. So let's say this is 5 meters per second, and it's going into an area where it travels 4 times faster, okay, at 20 meters per second. All right, so these waves are speeding up. And the point we're interested in is where theta 2 becomes equal to 90 degrees. So when this is big enough that this is 90 degrees, any angle larger than that, they'll have this total internal reflection happening. So let's set our formula up here such that we can figure this out. Okay. So what we want, okay, is we want this value, sine theta 1, which we're going to call the critical angle. Okay. And sine theta 1, the critical angle, happens when sine theta 2, the refracted angle, equals 90 degrees. Okay, and V1 we said in this case was 5 meters per second, and V2 we said in this case was 20 meters per second. Okay, and actually just before we put actual numbers in, we should derive what we want. Now remember that the sine of 90 is 1, so just before we do that, we could say this. The sine of 90 is 1, so anything divided by itself by 1 is just itself. So you end up with this. So this is a way of, I guess, shortening up to find your critical angle. Your critical angle happens as essentially this formula, right? So if that equals 1, we end up with this scenario right here. And if we want to find the angle by itself, we have to do the inverse of sine here. So we do the inverse of sine to both sides, we end up with this. Okay? And so, just in its general form, looks like that. Okay? So let's figure out what number we would actually get if this were the velocity relationship. Okay, so when you solve for this, it should work out to be about 14 degrees. Okay, so let's just quickly review what that 14 degrees actually means. So here we have an interface. Here's the normal. Okay, our waves are coming this way. Okay, they're bending away. And what we're saying is that this angle here, the critical angle, if you go above that angle, you're going to have total internal reflection. Okay, because at that angle, the refracted angle equals 90 degrees. Okay, and that happens at 14 degrees here. So anything larger than 14 degrees will cause total internal reflection. This is an extreme case. I don't think you'd probably really ever have such a large velocity change like in something like water. But it's more about just the idea of how this works. So in other words, if I hit this surface at an angle of 45 degrees or 50 degrees or even 15 degrees, those waves will not escape. So if I want to escape from here, I have to hit the surface at lower than 14 degrees. So 12 degrees, yep, waves will escape. 15 degrees, nope, they stay in. Does that make sense? Awesome.